Buddy, we're going to launch in today describing some environmental controls on kinetic rates that might be measured in a chemical system. And by the end of this video, I want you to be able to use the Arrhenius equation to predict reaction rates at different temperatures. And secondly, describe 4 factors that make apparent rates context dependent. So let's get into that. So the first control that I want to talk about is indeed the master control on kinetic rates, which is temperature. Temperature has an outsized influence on kinetic rates, and this might seem intuitive to you, but at hotter temperatures, reactions proceed faster, and at colder temperatures, reactions proceed more slowly. Now, why is this, though? Well, to make sense of this, we have to make recourse to the changes that molecules undergo as they proceed from reactants to products. So let's consider this plot here. On the x-axis, we have the progression from reactants to products through time. So this can be viewed as like a time axis. And on the y-axis, we have the energy levels of individual molecules that are participating in this reaction. So if you have a reaction A plus B yields C, this represents the energy level of one molecule of A and one molecule of B. And starting off, you can see that the reactants have some fixed energy level in the system. And in order to proceed from the state of reactants to products, they need to gain energy first. So gain energy before then coming back down and releasing energy as they become products. And the amount of energy that they need to gain above their baseline energy level here, so this distance here on this axis, is called the activation energy, or E sub A. And so if a set of molecules that are reactants gains a little bit of energy and it puts it up to this state here, that's not enough energy to get over this hump and come down to form products. So if they gain a tiny bit of energy, they'll just relax and come back down to being reactants again. It's only when they gain an amount of energy in excess of this activation energy that 2 molecules, A and B, can proceed to form their product molecule C. And indeed, the way that enzymes work is just by lowering this amount of activation energy. So with an enzyme or with a catalyst in general, any sort of catalyst will decrease your activation energy. And this results in a faster rate because reactants have to overcome less of a hump of activation energy to become products. But so what does this concept of activation energy have to do with temperature? Well, you can understand this by understanding that temperature is just a measurement of the mean amount of kinetic energy in a system. So different molecules in a system might have different energy levels, but if you sum up the energy levels of all those, or you take the average of all those energy levels, that is simply equal to the macroscopic property of system temperature. So the higher the temperature, the more energy individual molecules have. So let's consider this. If 2 molecules, this red molecule and this blue molecule over here, have relatively low kinetic energy, so they're not moving that fast. They might each individually be at a low temperature, or they just don't have a lot of kinetic energy. Then they come together, they just bump each other, and nothing happens. They just bump each other, and then they go on their separate ways. But you raise the temperature in the system, then these molecules might have more kinetic energy each. And so the higher temperature raises the probability that each of those molecules will have enough kinetic energy to supply the activation energy. And if they come together more forcefully, kablam, you have a reaction occur. So that is how temperature relates to the activation energy, which overall determines the probability that 2 individual molecules colliding will have enough kinetic energy to overcome this activation energy hump and produce the products in a reaction. And so this leads us to the Arrhenius equation, which should look pretty familiar to you because the Arrhenius equation is simply the Van Hoff equation with kinetic rates substituted in for your equilibrium constants K1 and K2, and the activation energy substituted in for your Gibbs free energy of reaction. So I don't want to get into a derivation of this formula, but it proceeds along the same lines as the Van Hoff formula is derived. And indeed, this formula was discovered as simply an extension of Van Hoff's research. And so this formula here relates a difference or a ratio of reaction rates, K, as respects a change in temperature over here, T2 and T1. So what you can do is, if you know a reaction rate K for a reaction at a specific temperature, say T1, just plug in T1 here, the temperature that you know the reaction rate for, plug in the reaction rate that you know here for K1, plug in the number that you want for the temperature of the system that you don't know the rate for, and then solve for this K, knowing the activation energy. And this is a value that you'll find published in various places, or which can be empirically determined. So just rearrange this to solve for K2, and voila, you have your reaction proportionality constant at the temperature that you wanted to know it for. So pretty easy formula to apply if you know how to apply the Van Hoff equation, so you can just review that if you need a little refresher. And it's important to note that this can be physical. It can describe elementary reactions, and in fact that's the context it was developed in describing elementary reactions. Or this can also just be an empirical measurement with an empirical activation energy that's been determined experimentally. And often this will be accompanied by having a little fudge factor because it's an empirical measurement and you just want to use this formula not to describe some underlying profound physics, but just to get the answer right. So be prepared to see these published with a fudge factor if you're ever using the Arrhenius equation in your work. And then finally, I just want you to note again that this is equivalent in form to the Van Hoff equation, just with different variables in different places. So now I just want to dive into something that is related to the Arrhenius equation, but is not exactly the same concept. And that's the idea of Q10. And this is something you see particularly a lot in biology. And what Q10 is simply the fold increase in a process rate that you see with a 10-degree increase in temperature. So say I went out and I measured a process rate, say the consumption of nitrate, which we've been using a lot, at 12 degrees. And this rate was 2 moles a minute. And then I increased the temperature of my system. What reaction rate would I expect, say, at 22 degrees, so a 10-degree increase in temperature? Well, if my Q10 is 2.3, just pulling that number out of thin air, I would just multiply 2.3 multiplied by my original reaction rate, which is 2, and I'll arrive at a predicted reaction rate of 4.6 at a temperature of 22 degrees, which was 10 degrees warmer than the temperature that I first measured the reaction at, 12 degrees. And so to calculate this, you simply plug in the two reaction rates that you know at set different temperatures, and then you plug in their temperatures here, and this formula will just give you your fold increase, your Q10, for that reaction. And you see this a lot in biology. It's used to describe like cell growth a lot. And so in chemistry, you'll often see a Q10 value associated with chemical reactions that are associated with microbial metabolisms, or just any sort of animal or plant or microbial metabolism. And it's important to note that there's no physical basis for this formula. It's strictly empirical. These formulas generally have a very limited domain. It might work between, 5 and 40 degrees, but outside of that temperature range, these formulas blow up. Either your organisms die because it gets too hot or they freeze. And so generally there is a limited range in which these Q10 values hold, so it's important to recognize that when you're dealing with these values. So there are a lot of restrictions. There's no basis for it really in any sort of chemistry or physics, and they don't work except at within a restricted range of values, but they're very commonplace in biology. So I just wanted to cue you guys into this because there's a definite possibility that you'll see these in your work. Okay, so the second factor that I want to talk about with regards to environmental factors that can affect K values or reaction rates is surface area. And this should also seem pretty intuitive to you just by this following example. Which will dissolve quicker? Is it granulated sugar or is it rock candy? Of course, the granulated sugar will dissolve a lot quicker in some water. And the reason for that is simply that the granulated sugar has much greater surface area than the rock candy. So higher surface area relative to mass will greatly increase reaction rates for reactions that involve an interaction between a solid and a liquid. And as you'll see in this class, many of the reactions that we study indeed involve transfers between solid phase and liquid phase. And because of this, for reactions that involve solid aqueous interactions, almost all the time, these K values that you'll see published in the literature are published in units of per meter squared, so a surface area, per time. So they'll have like per meter squared per hour, per meter squared per day, something like that. So it's vitally important to always keep in mind the surface area of the reactants you're dealing with. And say if you're dealing with a mineral that's ground into a fine powder versus one that's in rock form, you'll always have to account for that when accounting for kinetic rates in a system. So the third factor that I want to discuss is the impact of transport speed, which is important when you're considering, again, interactions between a solid phase and an aqueous phase. And so let's just take this example above. Say you have a solution flowing over a reactive surface. This is a reactive surface, and the solution is flowing this way. And you measure a K value simply by measuring the concentration here and the concentration here, and then dividing by the time that it takes for the aqueous phase to flow over the solid phase. That will give you an apparent K value. That apparent K value, though, is highly dependent on the speed of this flow. Why is that? Because as the solution flows over this reactive surface, the concentration of the reactants decreases from high over here to low over here. And so as that concentration decreases, the reaction rate also decreases. So actually when you produce an apparent K, just from measuring K here and here, what you're doing is you're actually integrating over the rates that are occurring over this entire concentration gradient. So if you speed up the flow, what's that going to do? Well, then the water is going to be moving faster across the surface than this reactive surface can consume it. And so this is going to increase the concentration along this entire reactive surface. And thus, you're going to have a higher apparent K value because the concentration remains higher across the entire length of the reactive surface. By contrast, if you slow down the flow, you're going to move the consumption of all of the reactants further to the left on this flow surface, such that maybe like you use up all the reactants by the time that the water reaches here on the surface. And so this will result in a lower apparent K value for your reaction, simply because you've changed the concentration of reactants in solution by varying the speed of the flow at which those reactants pass over a reactive surface. So this is very important for interactions of minerals with solutions. And it's super important for soil and rock geochemistry. And we're going to read a little bit about this more in a paper by Kate Mayer and some other people. So this is an example of advective or directional flow here. But we can also consider this in a turbulent case where a reaction center is a point in space. Now, where is an example where this might happen? Well, consider a microbe that exists in a solution. That microbe will consume, if it can, through its metabolism, consume some reactants around it, lowering the concentration of reactants in its immediate vicinity. So the concentration of reactants immediately surrounding a microbe will be lower than in the bulk solution, just because the reaction, according to the microbe's metabolism, is progressing and consuming reactants. And so again, you get a concentration gradient set up with low concentration immediately around the microbe, high concentration in bulk solution. And again, the severity of this gradient will depend on the amount of flow that's occurring, in this case, turbulent flow. So if there's turbulent mixing, that's coming and just mixing up the water in the immediate vicinity of the microbe. If there's a lot of turbulent mixing, then you'll have a very shallow concentration gradient. The concentration near the microbe will almost equal the concentration in the bulk solution. Whereas if you have very slow or no mixing, then you'll end up with a very steep concentration gradient. And with a steep concentration gradient, the apparent K that you measure for a microbial process will be a lot lower because the concentration around the microbe is lower. Whereas with a lot of mixing, if you're facing this concentration gradient and the concentration near the microbe is relatively high, you'll have a relatively higher apparent K value. And so this is kind of the operating principle behind continuously stirred tank bioreactors, which is, a technology where you add reactants into a tank with some microbes that can do whatever reaction that you want them to do, and you stir it continuously. And the stirring of that reactor continuously results in the reaction proceeding in a faster rate, simply because you have more of the reactants getting in closer contact with the microbes, because you have all this turbulent mixing that's continuously happening in the system. This is something that happens in wastewater treatment plants. And it's also the same principle as why stirring your sugar in your coffee dissolves it quicker than just letting it sit at the bottom. Because when you let it sit at the bottom, you end up with a saturated amount of water-containing sugar immediately surrounding the sugar crystals that prevents further dissolution of the sugar. Whereas if you stir it up, you're reducing the concentration of dissolved sugar around the sugar crystals, and so that speeds up the dissolution reaction. So the amount of turbulent mixing around interfaces between solids, or in this case a microbe, and the surrounding supernatant aqueous solution can dramatically affect apparent rates of reaction. Okay, so the last example of transport speed influencing reaction rates, or apparent reaction rates, that I want to touch on is the idea of diffusion limitation at the aqueous solid boundary. And key to understanding this is the concept of the no-slip condition. And this is a concept from fluid mechanics. And the no-slip condition says that even if you have advective transport of some aqueous solution across a surface, so like just in this example we had advective transport, even if that's moving at a relatively fast velocity, a little bit of a distance away from the surface, so you have these arrows now represent flow vectors, so the larger arrows represent larger speeds of flow. Even if you have fast flow occurring at a slight distance from a mineral surface or any sort of solid surface, as you approach that surface, the speed of that flow asymptotically approaches zero, such that at the exact interface between the aqueous and the solid phases, you have an advective transport speed of zero. So water that's touching a mineral is actually not moving through advection at all. And the reason for this is that the adhesive forces of water, so the forces that allow water to stick to non-water molecules, is stronger than the cohesive forces, or the forces that allow water to stick together. So this is a key concept of viscous flow. If your cohesive forces are less than your adhesive forces, then at any boundary between a solid and a liquid phase, you're going to have zero flow at that boundary, even if the water flowing just a short distance from that aqueous solid boundary is moving quite rapidly. And so because you have no flow here at this exact interface, the only way that molecules can move to or from the surface of a solid is by diffusion. So you can actually have diffusion limitation. So there's no advection, but there's still diffusion occurring in the system. And you can actually have diffusion limitation that controls the rate of reaction. And this is super important for things like sorption mechanisms and a lot of other chemistry that we'll discuss later. So even if you have very, very rapid rates of advective flow moving over a surface, your ultimate control on your rates can be how fast the products of a reaction can diffuse away from a mineral surface where that reaction is occurring, and how fast the reactions of a reaction can migrate down to that surface via diffusion. So the last factor that I want to discuss as something that can influence apparent reaction rates that you measure empirically is the presence of other reactants or products or solutes in general in your system, or the presence of other reactions that you didn't know were occurring or affecting your reaction. And perhaps the most important one of these that you always have to take into account, basically, is pH. And this is because many, many chemical reactions involve either protons, H+, or hydroxyl groups, OH-. And so pH can exert a very, very strong control on reaction kinetics, simply because these are products or reactants that need to be taken into account in your reaction rates. And so, for example, this graph of calcite dissolution shows that pH is a master control on calcite dissolution rates for one domain. So look, right here, there's a very strong relationship between calcite dissolution rates and pH, whereas out here, it doesn't really matter all that much. So if you're perhaps looking at values in the literature for calcite dissolution and you don't consider the effect of pH, if you use values from over here, you're probably safe up until some pH, like around pH 6 or so. But say if you want to consider calcite dissolution at a pH less than that, then your result from using this value is going to be way off because you never considered the effect of protons in your reaction rate. And indeed, this can have such a dramatic effect that the equilibrium of your reaction can be reversed, and you'll actually have production of reactants and consumption of products. So pH is a super important control on a lot of reaction rates that has to be taken into account when you're considering either literature reaction rates, or if you've empirically measured reaction rates, you have to take note of the pH most times and consider how your reaction rates are going to change if you change the pH of your system of interest. The next thing I want to talk about is just other reactions that could be occurring that you don't even know about. So we've talked a lot about the removal of nitrate in this lecture series, simply because that's something that's very important for water quality that's kinetically controlled. And the primary pathway by which we remove nitrate from water is this process of denitrification, which is shown up here, starting with nitrate and moving to dinitrogen gas. But there are a ton of other processes that can influence nitrate concentrations and nitrogen concentrations in a system. And so you have all these other removal processes that are occurring over here that aren't necessarily related to denitrification. And you have all these production processes that can be adding nitrate into your nitrate pool. So if you measure an apparent rate, you're not measuring just the removal of nitrate via denitrification, but you're actually just measuring the sum of these reactions. And so if you do something that speeds up one of these reactions, but doesn't affect this reaction, your K value will decrease. So it's always important to consider what all the reactions are that are occurring that increase or decrease your concentrations of products and reactants in your system when you're using that to determine an empirical K value for a reaction or an empirical rate constant. The second thing that's vitally important to consider is the presence of catalysts in the environment. So here are hematite nanoparticles, and hematite is a vitally important catalyst for the degradation of organic compounds. Organic compounds will absorb to the surface of hematite crystals, and this results in their very, very rapid decomposition compared to decomposition in the natural environment, such that the sorption reaction actually can be the rate-limiting step in a reaction of degradation of organic compounds. So if you don't have hematite in your system, you might notice very slow degradation, but if you have even like a very, very low level of hematite in your system, that reaction rate might accelerate very dramatically. So if you're taking rates measured in one system and applying it to the other, you have to make sure that there hasn't been a change in the amount of catalysts that exist in the environment that can catalyze the reaction of interest that you're following. And indeed, lots of times when we try and modify reaction rates in a system, in engineered systems, what we're doing is we're simply modifying the presence of catalysts so as to dramatically speed up that reaction rate. So that kind of wraps up my summary of environmental factors that can come into play in determining overall reaction rates, both mechanistic rates and especially empirical rates. And these are just things that you always need to keep in mind and little caveats that you need to check out for when you want to take the results of one reaction rate experiment and apply it to a system of interest. You always have to keep your context in your mind and make sure that you're accounting for context when you're applying reaction rates in different situations. So thanks for listening.